All right, so in this problem, in this video homework, I ask you to provide the product and give the mechanism. So there's a reaction here, organic compounds, some reagents, some solvents, some temperatures. Again, in the reaction arrow, anything over the reaction arrow is simply basically added in. You can read this as this compound plus triethylamine in DMF or plus DMF. DMF is a solvent at 100 degrees. So you're just throwing all this stuff together. And I ask you to provide a product. Product's self-explanatory. What are the chemicals that result from this reaction? And what is the mechanism? So by mechanism, when I ask you for the mechanism, I'm asking for E1, E2, SN1, SN2, acid base, rearrangement, and you could draw it, but you could just give me, you could draw the mechanism, or you could just tell me E1, E2, SN1, SN2. Okay, so how to do this problem? Well, take a look at your organic compound. I've written it sort of below here. It's a sulfonate ester. This could be O-mesylate, so it's a sulfonate ester with a methyl here. And you should see, if you haven't seen it, there's a little mini lecture and tutorial on hydroxide or OH as a leaving group that you should look at that explains these sulfonate esters. So you have a leaving group on a secondary carbon. I'm going to erase this mesylate thing down here now. So leaving group on a secondary carbon. Do you have a strong base or a good nucleophile? Remember, that's, so you have a leaving group. There are beta hydrogens, right? There's another hydrogen there, so that's a beta hydrogen. Actually, that's not a beta hydrogen. Sorry, my apologies. That's the alpha carbon. Leaving group is on the alpha carbon. We have two beta hydrogens. Okay, so elimination is possible. We have a leaving group, so we can do substitution or elimination. Do you have a good base, a good nucleophile or a strong base? Triethylamine, right? You should think about this like ammonia. And so triethylamine, it turns out, is a pretty strong base. So it's a nitrogen with a couple of ethyl groups. So it's a strong base, and it's a sterically hindered strong base. So a strong base that's sterically hindered is typically not going to be good for doing a substitution reaction. So sterically hindered, not just asterically. So this sort of suggests E2. Triethylamine can also be a nucleophile. It can be a nucleophile, but it's a better base. Polar aprotic solvent, that supports E2, SN2 over SN1, E1. And we're doing this at a high temperature. E is usually faster at high temps. Okay, so all of this suggests we have a secondary, leaving groups on a secondary carbon. SN2 is possible, but slow. Right? Because the more sterically hindered the electrophilic carbon is, the slower SN2 will be. So we have a strong base, we have a high temperature. So strong base is going to suggest E2, SN2 over SN1, E1. SN2 and E2 are faster than SN1 and E1. So a strong sterically hindered base suggests E2. Polar aprotic solvent supports E2. High temperature favors elimination. So this is probably going to be an elimination. Mechanism will be triethylamine will grab the proton, make a pi bond, kick out the leaving group. And the products can be cis or trans, right? You're going to make a double bond here, going to lose the leaving group. The ethyl group can either be trans to the methyl or cis to the methyl. Zaitsev's rule would tell you that this will be the major product. The trans isomer is more stable than the cis, and that the mechanism is an E2. All right, so you're going to see a lot of problems like this, and that's, you want to work through that flow chart to get you to a product and a mechanism. All right, there'll be more of these.